So in this video, we're going to be discussing what I call the simple gas laws, which is that we're only looking at the relationship between two of three variables. And so what might those variables that we would want to consider in association with gases? Well, we're going to be looking at, the relationship between temperature, volume, and pressure. But in the simpler gas laws, we're only going to be looking at two of these three variables, and we're going to perform controlled experiments, keeping one of the variables constant. So, like for instance, in this first law, which is Boyle's law, Boyle performed experiments to look at the relationship between volume and pressure. And so we've learned in science that if we want to see if there's a relationship between two variables, we can't be changing any other variable. We want to control the circumstances. And so Boyle, in his design of a controlled experiment, kept temperature constant, so that he recognized that if he did that, then any relationship between volume and pressure could be attributed to that and not necessarily to any temperature changes. So let's think about what we already know about the relationship between the volume and the pressure of a gas, right? So let's just say, for instance, and I'm just going to draw a little picture here, that I had particles of a gas in a syringe. Okay, so you know what I mean by syringe. Just you might have it for medicine or for a needle, right? But typically, what it has is some sort of depressant, like depressor or whatever, and so the gas would be sort of filling up the area within the syringe. And so in class, I'll show you this, but I have this special syringe where the end is blocked off so that the air can't escape. Okay, so really with the depressor at the top and with the blocked end at the end, I can control how much air is, how much the volume of air in that syringe. So I want you to think about your own experience with this, right? So let's say, for instance, I go ahead and I measure out, let's say the volume here is arbitrarily, let's say about maybe 10 milliliters. I'm just totally making this up. And then what I do is I go ahead and I depress it. So I'm just going to depress that down so that the new volume of the gas is 5 milliliters, so half the original volume, right? So what would I expect to happen, or what would I feel with respect to the pressure as I compress the gas to a lower volume? So in other words, what happens to the pressure in that syringe if I decrease the volume? Okay, so I've decreased the volume. What's going to happen to my pressure? So take a minute to think about that. Well, what I'm hoping that you thought about was that if I depress that syringe, all of a sudden I'm going to feel a lot of pushback from the air, and that is an indication that the pressure has increased. So by decreasing the volume of the container, I've actually increased the pressure. So, and that's what Boyle found. Boyle found that when he increased the pressure, the volume went down, and when he decreased the volume, the pressure went up, right? So let's see what that looks like on a graph. We can think about this in mathematical terms, right? So what he saw was that as the pressure went up, the volume went down. We say that this is an indirect or inverse relationship. Okay, so we say P is proportional to 1 over V. So in other words, as the pressure goes up, the volume goes down. So now this little bit that I've indicated, this looks like a fish almost, that is what we call a proportionality constant. Let me see if I can write this up. Proportionality. Nope. Let me try that again. So proportionality constant, it's not exactly an equal to, it just means that they're related in some way, okay? So often what we do in math and in science is we collect data and we see how it's plotted and what the data looks like, and then we can create equations or formulas from that, right? So the way that in math you are able to convert a proportionality to an equal sign is you sub in a fudge factor or a constant, a proportionality constant. So I can kind of make this an equation by saying P is equal to some constant, I'm just using the variable K, times 1 over V, right? Now let's look at this. I want to go back to this first equation, or this first relationship here. P is proportional to 1 over V. Well, I'm hoping that you recognized that that looks a little bit like something you might have seen in math class, which is that y is equal to 1 over x, a rational function, right? And so rational functions have asymptotes. So if I were to plot, let's say, for instance, P versus V, then what I would expect the graph to look like would be something like this. So that as the pressure goes down, the volume goes up. And so that graph should hopefully make sense. And that's essentially what Boyle did, was he measured he controlled the volume and he measured the associated pressure of a gas at a variety of different volumes. He said, okay, well, and then he used that data, plotted it on a graph, and saw that it created that rational function, right, based on the line of best fit. Okay. So as we said before, and you'll want to get this in your notes, that pressure and volume are said to have an indirect or an inverse relationship. So in other words, as one of the variables goes up or is increased, the other one goes down or is decreased, right? And we saw that with volume and pressure. So that allows us to create an equation. And so I'm just going to go back for a second here, and we're going to write down an equation. So in developing an equation to relate pressure and volume, we know that it's indirect, right? And so usually we're talking about, in cases where we're examining the gas laws, we want to know, well, what happens if we have a certain initial set of conditions for a gas, right? So, the initial conditions of pressure, I'm going to call that, like, let's say pressure 1. And the initial conditions for volume, I'm going to call, volume 1. And then, I might change one of them, right? And I want to see what the effect is on the other variable. So let's say, for instance, I change the pressure and that there's a new pressure. I'm going to call that pressure 2. And then what the question might be asking me, well, what will the new volume be? What will V2 be? Okay? So now, so those are our variables. And so we know that there's an indirect or inverse relationship between pressure and volume. So I know that my pressure 1 is going to be proportional or equal to 1 over my volume 1, right? They're on opposite sides of the fraction. So in the same way, my final pressures and volumes are going to be inversely proportional, right? So my P2 is going to be inversely proportional to my V2. And so what I've done here is I've created this formula that allows me to connect initial pressures and volumes to final pressures and volumes. And so that's our first of 3 equations in this section. All right, so let's look at a first example here. The first example says a 2-liter flask is under 105 kilopascals of pressure. It is evacuated into a 3.5-liter flask. What is the new pressure? So it's important to mention here that in the formula we just developed, we want to ensure that our units for pressure are kilopascals. So in this question, we're fortunate because they are giving us our units of pressure in kilopascals. Now, there are going to be multiple variables in these in these problems that we're going to be working through. So I'm going to suggest we go back to our foundation from grades 9 and 10 science, which is to use a sort of modified grasp method. So we're going to write out our givens. Okay, so you may find it helpful to use a highlighter if problem solving is something that you struggle with, and to highlight each of the measurements that you have in a given question. So, and then that might help you to sort it out. So when I look at this question, I'm reading that I'm starting with a 2-liter flask, and liters are a unit of volume. So that is my V1. So I'm going to write out that V1 is equal to 2 liters. And I need to put the 2.0 there because of significant digits. And it says it's under 105 kilopascals of pressure. So that is my P1. Okay, and it says it's evacuated into a 3.5 liter flask. So I'm changing the conditions and I'm increasing the volume. So my volume, my V2, is 3.5 liters. And finally, the question finishes with, what is the new pressure? So I'm looking for P2. P2 is my unknown. So there I've written out my givens, and that allows me to see, because we will have multiple equations in for the rest of this unit, this lets me to narrow down which of the formulas that I need to use, right? And so I know that as the volume goes down, the pressure goes up. So my volume went up, I'm going to expect that my pressure value for P2 is going to be lower than my 105 kilopascals. Okay, so the formula that I gave you, that we worked through, was this one. P1 over P2 is equal to V2 over V1, right? Now these are both fractions, and so I know that the reciprocal for each of this equation will also be valid. So for instance, if I were to say to you, is 1/2 is equal to 2/4, right? That's certainly true. Well, what about if I take the reciprocal of both sides? Does the equation still hold true? Well, 2 over 1 is equal to 4 over 2. So the left side of this still equals the right side, which means that it was perfectly valid for me to take the reciprocal and still have the formula relating pressure and volume be valid as well. And so that's what I'm going to do. And you're going to see why I'm choosing to do this. So I'm going to actually rewrite this formula by flipping the equation to have my unknown, my P2, in the numerator. That'll make my equation, that P2, easier to isolate, and you'll see what I mean in a second. Okay, so I'm going to write this as P2 over P1 is equal to V1 over V2. Now I'm going to substitute in all of my values that are known into my formula. So P2 over 105. And I'm okay with you including the units in your formula. I think that's appropriate. V1 is 2 liters, 2.0 liters. And then my V2 was 3.5 liters. And if I do my unit analysis, I can see that my liters here will cancel out liters divided by liters, and I'll be left with units of kilopascals, and so that is dimensionally sound. Okay, and so now I want to isolate P2. So this is my P2. I want to get that by itself, which means that I need to multiply out my 105 kilopascals. I'm going to bring that upstairs and multiply. And so when I go ahead and do that, I get a value for P2. I'm just working this out on my calculator. And you can double check that the answer ends up being, right, so 2.0 divided by 3.5 and then times 105 gives me 60. So I'm going to do my unit analysis here and see that my answer should have 2 sig figs. So I'm going to write that as 6.0 times 10 to the power of 1, and my units are kilopascals. Okay, hopefully you found that okay. What I'd like you to do now is to pause the video and work on the first couple of questions on the worksheet that's posted for Google Classroom. And when you're ready, return to the video. So let's look at the second of three gas laws, which is called Charles' law. So what Charles did is he kept pressure constant. And so he was looking at the relationship between temperature and volume, right? So that's what he looked at, temperature and volume. So let's conceptualize this. Let's think about this before we do anything else, right? So let's just say that I have a certain amount of gas, right? So I'm going to just I'll just draw these little gas particles, right? And so let's say they're in an open container, right? And let's say that container is a pot, and I have it on a stove, and then what I do is I heat it up. So I'm going to heat it up. Well, so in other words, I'm increasing the temperature, right? So I want you to think about, well, what would happen to the volume of that gas? Right now, that gas is sort of nicely, sort of probably, more or less, if this is a pot of boiling water, it might be just sort of there on the surface, right? But what do you think will happen to that gas if I increase the temperature? Well, if the temperature is high enough, hoping you recognize that the volume of that gas is going to increase, because once the temperature is raised, those particles will gain a lot of energy, and so then they can overcome the forces of attraction that exist between them, keeping them kind of holding them together. They can overcome those intermolecular forces of attraction, and that allows them to move away from each other and to spread out, and thereby increasing the volume of the gas. So in other words, Charles found that volume and temperature were directly proportional, right? So in other words, as the temperature went up, the volume went up. They are directly proportional. So we would write that as T is directly proportional to V, or V is directly proportional to T. So remember, in the last little section of the video, we talked about how we take a proportionality statement and we make that into an equation. Well, we insert a proportionality constant, which I'm going to use as K. So let's look at this. I want you to think about grade 9 math for a second. And I want you to think about, well, what kind of relationship is this? This is saying, well, this is kind of a linear relationship, isn't it? This is like saying y equals mx plus b, right? So because I don't see any exponents at all on my variables, so that leads me to believe that this is linear. And in fact, if you were to plot temperature versus volume, temperature versus volume, you would see that it is indeed a linear relationship, right? And so in this case, it just so happens that my y-intercept is 0. And that should make sense, because if there is, 0 volume, then there's nothing to have a temperature, really. Okay, so now I want you to take a minute, actually, and I want you to come up with what you think an appropriate equation would be to relate temperature and volume. So hopefully when hopefully when you thought about this, you were able to come up with a formula that makes sense. So I saw here that volume and temperature were directly proportional, which means that, an initial temperature, which I'm going to call T1, which should be on this, directly proportional to my V1. And so on the same side of a fraction in a formula. And so if I go ahead and I change the temperature, T2, that I should be able to get a volume, V2, from that as well. So you can see a couple of things here in terms of the trend. See that temperature is still, T1 is still directly proportional to V1, and T2 is still directly proportional to V2. And so my equation is set up that way. All right, let's try a problem to help us work through this. Now, I should mention to you, and we should include this in our notes, that our temperature needs to be in Kelvin, okay, not Celsius. Because if we had negatives in here, that would mess up our values, and we'd end up with potentially a negative volume, which makes no sense. There are other reasons, but that's as good as any. So here's a question that I would like for you to try on your own, and that when you're ready, we can take up together. Okay, so pause the video now, try the question, and then see how you do. Okay, so I'm going to highlight some of my givens here. I'm given 6.67 liters, and that is an initial volume. So I'm going to call that V1. Oops, let me switch to a different color. Okay, so V1 is equal to 6.67 liters. Okay, my T1, I'm going to assume is in this question, is 37 degrees Celsius. So I remember that I can't have my temperature in degrees Celsius, so what I'm going to do is I'm going to convert that to Kelvin by adding 273 to that value. And so when I add those two together, I have my temperature that I'm going to use in this problem, which is 310 Kelvin. Okay, let's continue to look at the problem. I'm cooling it to 12 degrees Celsius, and I want to know the new volume of the gas. Okay, so my T2 is going to be 12 degrees Celsius plus 273, so 283, 285 Kelvin, and I want to know V2. Okay, hopefully you did okay with that. Now let's look at the second part of this question, which is to say, well, I'm seeing that I'm working with initial and final temperatures and volumes, so I need to use Charles's law. And V2 is my unknown, so I'm going to write my equation with V2 in the numerator, because that just makes it easier to solve using fewer steps. So V2, and I'm just going to remember that temperature and volume are directly proportional, so my V2 and my T2 need to be on the same side of the fraction. Now I'm going to substitute in all of my known values. V1 is 6.67 liters. My T2 was 285 Kelvin, and my T1 was the 310 Kelvin. Okay, so remember I'm wanting to isolate V2, so that means this 6.67 is going to go upstairs, and I'm going to multiply it by the 285 over 310. And so I get an answer there for V2. Let me just work my magic with my calculator here. 285 divided by 310 times 6.67. And I'm getting 6.132 blah, blah, blah values. And so I'm looking at my values in the measurement, and 310 has 2 sig figs, so I'm going to round that to 6.1 liters. And there's my answer. Hopefully you did okay with that. But if you have any questions, feel free to ask for some help when I get back to class. So now you should be able to work on a couple more of the questions from the worksheet that was handed out. And when you're ready, come back to the video and resume it so that you can learn about the third and final simple gas law. So the third and final gas law is Gay-Lussac's law. And so what they wanted to figure out was, well, what is the relationship between temperature and pressure? So volume was kept constant, and temperature and pressure were examined, right? So let's think about that before we kind of go any further, because I want this to make sense to you. I don't want you to just be memorizing these rules. You should be able to think logically about the variables that are at play here, right? So I'm going to think about, let's say, I don't know, one of those aerosol cans, right? So if I had one of the aerosol cans, I think we all agree that's a really crappy picture, but whatever, it works, right? I think we can all agree that, you know, you don't want to put one of those on a fire, right? On a bonfire, and there's some very good reasons for that, right? So if I were to put it on a bonfire, then what would happen? Well, I'm increasing the temperature when I do that, first of all. But the problem is that this is a fixed volume container, right? There's only so much that it can expand before it explodes, right? And I think we all recognize that as the temperature goes up, these particles are going to be bouncing off the sides of that container at a higher rate, right, because of the extra energy. And so that is going to cause the pressure to go up. So in other words, if you increase the temperature of a fixed volume, a material in a fixed volume container, then the pressure is definitely going up, right? So much so that, in fact, this summer that happened to us in our fire pit. We accidentally put a spray can in the fire when we were just dumping a bunch of garbage, and it did make a nice loud boom because of the pressure. So my advice to you, don't do that. All right, so that is, let's explore this a little bit more. Okay, so Gay-Lussac, he kept volume constant and tried to see what the relationship was between pressure and temperature. Okay, so if temperature and pressure are directly proportional, then we should be able to see a linear relationship, a linear relationship when we plot pressure versus temperature on a graph. So I want you to take a minute and come up with what you think would be an appropriate equation here. I'm hoping that you were able to come up with a P1 over P2 is equal to T1 over T2, or something similar. Okay, what I'm hoping that you noticed is that because it's directly proportional, the initial conditions are on the same side of the fraction, and the final or secondary conditions are on the other side of the fraction, but on the same as each other. Okay, let's try one final question. I'm going to leave you to try this on your own and then to start the video again when you're ready to take up the question, just to see how you did. All right, so I'm going to take up the question now. So it's saying a gas at STP is heated to 298 Kelvin. What is the final pressure of the gas? So you'll remember that STP, by giving us that set of conditions, we have both the temperature and the pressure in that statement. So that is telling me that T1 is 273 Kelvin. Standard pressure is our initial pressure, and that was 101.325, or just 101.3 kilopascals. And so those are values you're just going to have to memorize. And so it tells me that it's being heated. So heating is a temperature change. It's being heated to 298 Kelvin. What is the final pressure? What is P2? Okay, so there are my givens. And so since P2 is my unknown, I'm going to write my equation in the form where P2 is in the numerator. P2 over P1 is equal to T2 over T1. I'm going to sub in my unknowns. P2 over 101.3 kilopascals is equal to 298 Kelvin divided by 273 Kelvin. So again, I'm going to isolate P2 by bringing my 101.3 upstairs. And when I do that, I get a value for P2. I'll grab my calculator here. So 298 divided by 273 times 101.3. And when I go through that, just looking at all my variables, I should have 3 significant digits here. And so when I round to the appropriate number of significant digits, I get 111 kilopascals. And so there I go. So now you should, after going through all three of the simple gas laws, you should be able to complete the entirety of the worksheet that was given out on Google Classroom. And so that will be your homework for today. So if you have any questions about any of the worksheet problems or anything discussed in this screencast, feel free to give me write those questions down and we can discuss in class.